Hello, welcome to this episode of the Classics. Today we'll be taking a look at question 17, binary relations. So let's have two binary relations, phi and psi. I call E the space with the imaginary part of Z being super or equal to 0. So I call phi, phi in E, so in this space here, with for z prime in e squared, phi of z prime is equivalent to either the module of z is inferior to the module of z prime, or parenthesis their modular equal and the real part of z is inferior to the real part of z prime, and then I call psi, and then I call psi, thank you, is in R plus star with for x, y in E squared, it's not the same E actually. It's another E, because actually I took two questions and I didn't notice that it was called E. So this would be equivalent to, if there exists n an integer so that y is equal to xn. So we're going to try to see if these relations are relations of order and if they are total. So let's go to number 17. 17. Wait, where is it? So I take three elements of E3. So if we have that, well, I take Z. Z as its own is equal to its own module, and its real part fits this condition. So phi of zz is always true. So phi is reflexive. If phi of zz prime and f of it's z prime z here, it's just a bad copy pasta. Yeah. So if we have this, then their modules are equal, and then their real parts are equal. So so they are equal because they are in the same space. Their modules are equal. Their real parts are equal. So phi is antisymmetric. So then we suppose that we have this and this. So phi of zz prime and phi of z prime z second. So if we have z modulo of z inferior to modulo of z prime, it means that we have this in all cases, and we have the equality of the module. Then we have this equality here, and for the real part we have this inequality because of this hypothesis. So we have phi of z prime z second. So phi is transitive. In conclusion, phi is a relation of order. So we can compare z and z prime using phi. So if the module of z is inferior to the module of z prime, then we have phi of z prime. We have the same thing just by swapping z and z prime. If their moduli are equal, we have the same thing, but with the real part, and we still have the relation phi. And then if you swap z and z prime, we have the same thing. So all elements of E can be compared by phi. So this relation is total order in E. So now for the second question, we consider three elements of r plus star 3 to the power of 3. So if psi_xy and psi_yx, there exists nm to be equal to nm positive integers to be equal to have this, so you get this. So then I replace, so we get this, we get that x is equal to x to the power nm, and then I do this, and then I just take the logarithm, and we get this. So we get this, sorry, we get this inequality, this equality by doing minus ln x on both sides of the inequality. So once we have that, we have two possibilities: either x is equal to 1, but y is equal to 1 too, so it's true, and either x is equal to non-1, so it means that nm is equal to 1, so m is equal to 1, so x is equal to y. We get this because these are natural integers. So psi is antisymmetric by this. So now we suppose three elements so that we have psi of xy and psi of yz. So there exists nm in n squared, so that we have this. Then we replace, so we have z to be equal to x to the power nm. So psi is transitive, and so psi is a relation of order in n plus star. But however, we cannot say that it's total order because if we, oops, that's a typo. If we take 2 and 3, they cannot be compared using this relation, because 2 cannot be written as a power of 3 and vice versa. So this is not a total relation. So that's it. If you have any questions, feel free to ask them in the comment. I'd be glad to answer them. And bye.